I'm especially happy to announce a compatriot, Jacques Vanneste, with a truly Flemish name, who will speak about large deviation approach to advection, diffusion, and reaction. Thank you.
Okay, so this is a talk about joint work with Peter Haynes, who said he would be here, but he's not. And Alexander Tsela, who was a postdoc of mine and is now in Birmingham. So this is about applying large deviation to a very simple physical system to try to draw some conclusion about what is happening when you release some scalar, some chemicals, say, in a fluid flow. Okay, so this problem of releasing a passive scalar in a fluid flow has many applications in industry and in the environment. So I chose the pictures to fit the theme of the conference. So this is the oil spill in the Gulf of Mexico. You can see the oil swirling around with the flow, and this is the Icelandic volcano ashes at two different times. Okay, so this is just to motivate studying advection diffusion, because the concentration of the passive scalar is just, this evolution is governed by the advection diffusion equation, which I wrote here. Okay, so that you can get my notation. So C is the concentration, U the velocity, which is going to be prescribed, and divergence free, and kappa is the diffusivity. So I'm not telling you much you don't know if I say that if the initial condition is just a Dirac, or in fact if it's only normalized, we can think of this concentration as the PDF for the particle, the single particle position in this flow. So the particles will evolve according to this SDE, right? So just advection by the velocity, and then diffusion corresponds to this white noise term. Now, there's an awful lot of literature about the combined effect of advection and diffusion, because what people realize that if you start moving around the fluid, then particles tend to spread much faster, as you know when you stir your coffee. And lots of this literature is about finding effective diffusivity. So there's a kind of observation that in many systems, which is essentially just the central limit theorem, that if you look, for instance, at the variance of the particle position, it grows linearly in time with a coefficient of diffusivity here, which is not the molecular one, but which is something larger, which stems from a combination of both advection and diffusion. So that's one view of effective diffusivity, is the thing which gives you the linear growth of the variance. Another is a bit stronger, is to say that even the concentration itself evolves as a Gaussian with the effective diffusivity sitting here, right? And so there's a lot of literature about computing this effective diffusivity in some model flows. Right. In particular, the model flow which lots of people have used is the cellular flow. So it's an infinite periodic flow made up of cells where the flow is rotating counterclockwise and clockwise alternatively, with separatrices which extend to infinity. Right. So this flow, in fact, for many other flows which are periodic, time independent, you can calculate in a semi-explicit way the effective diffusivity. So this flow has this stream function in 2 dimensions. So very briefly, I mean, how do you calculate the effective diffusivity for this flow? Well, the most standard recipe is to use homogenization, which is just kind of multiple scale approach to this. So you see the concentration has a leading order part which depends in space only over a very large spatial scale. So epsilon is a small number, which is just a formal parameter here. You just expand this. So to leading order, as I said, the solution depends only on the large scale, doesn't have any fluctuation at the scale of the cells here. And then you'll find that the next order correction solves some sort of elliptic equation which is forced by the leading order concentration. There's a so-called cell problem. You solve this cell problem, and then there's a formula which expresses the effective diffusivity in terms of this C1. Okay, so it's a well-known recipe. And for this particular flow, the main result in my mind is by a string of people who show that in the most relevant limit, which is that of small diffusivity, the effective diffusivity, well, first scales like the molecular diffusivity to the power 1/2. Okay, so in other words, the effective diffusivity is much stronger than the molecular one, well, because the flow does some work to facilitate mixing. But what is truly remarkable is that the prefactor here is known exactly. Okay, so this is due to SOA, so you can calculate this in closed form.
What is it,
Well, here, I mean, it's just a formal parameter here. I will not need it, but its interpretation is just a scale separation between the concentration profile, which spreads over many, many cells, and the cells themselves. Oops. I'm very confused by this. Right, now...
But the relationship between the epsilon squared and the epsilon is related to the presence of diffusion.
Yeah, so this is because of, I mean, this scaling is the right scaling because the behavior is diffusive over a long time scale, right? Okay, so this business of having an effective diffusivity, of having a model which is approximately diffusive, is of course limited. In fact, it assumes, like the central limit theorem does, that x over t to the 1/2 is of order 1, x of order t to the 1/2 and no bigger, right? So it will fail in the tail of the concentration for large enough distances from the point of release. This is not going to work. And you can see this very easily. For instance, if you think about a point which is much further away than the maximum velocity in your flow times time, essentially for that point, the velocity is not going to help move this point all this way. So what will do it is the molecular diffusivity. So you can convince yourself that for very, very long distances, the distribution should not be a Gaussian with the effective diffusivity. It should be with the molecular diffusivity. So clearly there must be a transition somewhere where the prescription, the result of homogenization, this effective diffusivity, fails. So what is then the right distribution? Well, it's given by the large deviation form. So if now you assume that x is not of order t to the 1/2, but all the way to order t, then the concentration has this large deviation form. So it's an exponential again, minus t, and then some function of x over t. So instead of being parameterized by just one number, the effective diffusivity, the concentration is now parameterized by one function, okay, the rate function. And so what I want to do is to sort of discuss several points. So first, how do you calculate this rate function for essentially any periodic flow? And then more specifically, what we've done is to calculate it fairly explicitly in this limit of small diffusivity for this cellular flow. Now, we'll also discuss the fact that once you've computed this rate function, you also, without knowing, perhaps solved a problem in chemistry, well, at least in advection diffusion reaction equation. So there is something which I'll explain, is that the results can be transferred to tell you something about front propagation in some flows. So what I want to emphasize, because we've heard quite a bit already about large deviation, and we will in the next few days, is that what I'm talking about here is large deviation where time is a large parameter. Okay, this is not a small noise large deviation, which many people use, related for SDEs to Friendly-Wenzel type of ideas. Although this will come back at the end of the talk. Right, so why would one want to do this, calculate those concentration in those tails where they are very low? Well, low concentrations can be important, right? So an example which can be used is the release of a highly toxic chemical. So the first molecule will kill you, so you don't care about the core distribution where everybody will be dead anyway. You care about what's happening in the tails, because you want to know, for instance, when you have to leave the area to avoid this tail, right? So that's an example. From a more kind of theoretical viewpoint, homogenization has been sort of extended by several people who are trying to calculate corrections order by order to it. Well, large deviation gives you a kind of nice general view of this and a way of interpreting those improvements. And then in the spirit of the workshop, it's an example of extreme event statistics. We're trying to find, if we think about the concentration as the PDF for the particle position, we're interested in the probability of particles traveling a very long way away from the point of release. Okay, so they have very extreme behavior. Now, just to kind of emphasize the first thing, this fact that low concentrations can be important is completely explicit in a very simple example of when you introduce chemical reactions to the problem. So for this particular reaction, so this is my advection diffusion equation, and then you add a logistic type of evolution for which 0 concentration is unstable and 1 is stable. So what that does is that the concentration, as soon as it's non-zero, it just jumps to 1. So this is a FKPP type of reaction. In those equations, there is actually front propagation. So if you just, so this is an example in 1 dimension, or in 2 dimension, but just a row of cells in my cellular flow, so there's a bunch of cells. If you put a bit of scalar with value 1 here and 0 here, a front starts propagating, making sort of interesting undulation as it propagates because of the periodicity. But overall, there is an average speed, c, and it turns out, as shown by Gardner and Friedlin, that the speed can be computed explicitly from the rate function of large deviation. So it's an example where the low concentration, if you like, so what is happening in the tail of the concentration has an order 1 effect, because the front speed is definitely a macroscopic effect. Okay. So essentially, all I'm going to tell you can be used to say something about front propagation speed for those FKPP type of reactions. Right, so let me show you how to derive the rate function. And essentially, there are two ways to do this. One is probabilistic, and the other one is sort of crude asymptotics. So since I assume that lots of you knew about probability, I've chosen to explain the crude asymptotics way, right, so to confuse you. So you start with the advection diffusion equation, and I've made it non-dimensional, so my diffusivity here is gone, has been replaced by a Peclet number, which is a ratio between advection and diffusion strength. And what you can do is that you can just put as an ansatz the fact that concentration will be of this large deviation form, okay, where xi will be x over t, so kind of a speed, think of it as a speed, times some function, okay? So you just take that as an ansatz, you introduce into this equation, and you calculate, see what comes out, and here's what comes out, and then you realize that the g appears only in two forms. One is the grad of g, so then it becomes reasonable to call q the grad of g, because it's what appears here. And the other form is here, which we recognize as being the Legendre transform of this g, and I call it f. Okay? So this turns this problem into this one, just by kind of renaming things. And the way to think about it is that this is an eigenvalue problem. So you solve this for phi with boundary conditions. So for instance, for my cellular flow, this would be periodic boundary conditions. You solve this for phi, and for the eigenvalue here, f of q. You do that for a range of q. Once you found f of q, you invert the Legendre transform to get g, the rate function. Okay, so it's a very simple construction, except that this problem may be difficult to solve in general, so you use either numerics or asymptotics to do that. So this is the kind of first view of it, where you just treat this as an ansatz and it all works out. The other view, slightly more sophisticated, comes from the fact that there is this link between rate functions in large deviation and cumulant generating functions. So if you look at this cumulant generating function, for q being my sort of cumulant parameter here, for large time, this will increase like exponential f of q, okay, where f is the Legendre transform of the rate function. So this is an alternative way of thinking about this problem, and from this you can also derive the eigenvalue problem, which I wrote on the previous page. And one interest of this is that it also gives you a quick way numerically of finding this f of q. Because it's an expectation, you can just use Monte Carlo to do that. And as in the previous talk by Dan, so I've done quite a bit of Monte Carlo for this problem, and you have to use some sort of important sampling technique or something similar to the splitting, which they were using. So I've been using a pruning cloning, which I learned from Grasberger. Now a few more remarks. So when q is small, so q is a dual variable to xi. Xi is sort of velocity. Okay, so small q means essentially particles which are not too far away from where they were released. When q is small, then f, for this kind of flow which has no mean drift, f is quadratic to leading order. When you take the Legendre transform of a quadratic, you get another quadratic. Here it is. And then if you look at what this means, it means that the motion is diffusive. Okay, so for particles which are not too far from the center, the motion is diffusive, so we recover what homogenization tells us, and we recover that the effective diffusivity is just the Hessian of f with respect to q. Okay, so everything is under control. And also what this tells you is that essentially the procedure which I sketched to obtain the effective diffusivity can be obtained also by taking my eigenvalue problem and solving it perturbatively order by order in Q. Okay, so it's a kind of a nice way of seeing how you get to the cell problem. It also tells you how to generalize homogenization by carrying on the procedure to higher and higher powers of Q. Okay, but I won't be doing this. I'm going to solve the eigenvalue problem to all orders. Exactly. Okay, so back to the cellular flow. So I focused on that one for the talk. And I just want you to get a little feel for what the physics is, if you like. So I'm just going to show you a bit of simulation for the cellular flow at large Peclet number. And so there is a movie. I was surprised that it seems to be the first movie of the day, which says something about the kind of conference this is. So I release a bunch of particles in this flow. And what they do is that most of them are just on streamlines. Because diffusivity is small, they tend to stay on their streamlines. They go round and round. I should start that again. They go round and round. But then diffusivity makes them drift from streamline to streamline, and then every now and then they're kind of lucky so as to escape a cell and then can move to the next cell. Okay. Another way of thinking about this is just plotting a single trajectory, as is done here. And so what you see is that particles, well, a particle, single particle, is going to spend an awful lot of time in a cell, this one for instance, and then escape through a separatrix, go maybe to the next cell or a few cells down the line, and then start to kind of being trapped in the cell again. Okay, and so large deviation is going to tell you something about statistics of what's happening at long distances. For instance, a distance is so long that to make it, the particles cannot afford to waste any time in the cell. So they're going to have to stick to the separatrix to go a very long way. Kind of lucky particles which don't waste any time in the cell interior. Right, so another view is to plot the concentration field. So we just solved the advection diffusion equation in this problem for 4 different successive times. And so what you see, for instance, if you look at the last panel, is that the concentration is pretty much uniform in the cells which are close to the release point, but it jumps at from one cell to the next. This is something which is well known in homogenization theory, but if you go much further, say here, you'll find that there's some kind of interesting concentration within the cell, and then some high concentration along the separatrices. And if you go really far away, which you can't see, or you have to take a log in your head, if you go really far away, you'll find that there is some concentration, but it's completely confined to the separatrix, right? The cells are completely empty. And so I'm interested in sort of computing statistics of those particles which make it all the way to very large distances. Right. So you can do that just by solving this eigenvalue problem numerically. It's a two-dimensional eigenvalue problem, so you can discretize it, solve it, which I've done. And so what you get is the eigenvalue, which is this f. And I can compare to what I get doing Monte Carlo simulations, and I get the right thing. So things to observe are the following. For small q, so particles which are not far away from the point of release, things are axisymmetric, which is something you know from homogenization. In homogenization, the effective diffusivity that you get is just a scalar. It's proportional to the identity tensor. But if you go further away, then the dispersion becomes anisotropic. Okay, so you can see the isolines are not circles. And it's probably easier to think of this problem when you do the Legendre transform of this to get to this picture, which is the rate function itself. So the rate function is easy to understand, right? So you change its sign, you take the exponential, it gives you the concentration. So it's minus the log of the concentration. So what you see is that the concentrations are higher along the diagonal than they are along the axis. Okay, so particles have an easier way to travel far if they go in the diagonal direction than they do going along the axis. And you can kind of understand this very easily just by the kind of topology of the streamlines. Right. So this is purely numerical and a bit unsatisfactory. So what we wanted to do is to solve this problem for large Peclet using asymptotics. Okay, so we now have an eigenvalue problem. We should be able to just find a solution much more explicitly if we take advantage of the fact that the Peclet is large. The problem is not so trivial compared to homogenization, for which, as I've said, people have solved things very explicitly, have given an exact form for the effective diffusivity, because you now have this extra parameter floating around. So you have to solve a family of eigenvalue problems, not just one. And of course, the solution is not uniform in this parameter. So you have to start thinking about what are the values of Q which lead to distinguish limits, right, to sort of interesting balances in the equation. And we found 3 limits which cover the whole spectrum. So the first one is for Q of order Peclet to the -1/4. So I'll explain a bit more the calculation in each of these regimes immediately afterwards. But for the moment, this describes what's happening in what we've seen in the picture, where the cell interiors essentially, there's an interesting concentration distribution in the cell interior, and then there's also an interesting concentration profile in boundary layers around the separatrices. Okay, and so when you do the computation, you find that f is of order 1, but depends on this parameter. It should be actually a 1/2. Yeah. Then there's another regime where Q is of order 1, so this is going somewhat further away. And in that case, the cells are essentially empty. And so all that matters is the concentration within boundary layers around the separatrices. Okay, and then you get this more exotic scaling of Peclet over log Peclet, which I say a word about. And then finally, there's a regime where you go really, really far away, and that's finally the regime where it's a regime where you have to rely essentially on noise to get you all the way. Okay, and that's a regime which is controlled by also small noise, large deviation theory. So there's an intersection between large time and small noise, large deviation theories. Okay, so that regime you can actually find this f of q by using a sort of minimizing an action, so in the Friedlin-Wenzel kind of reasoning. Okay, so just a little bit more. So those 3 distinguished regimes correspond to are determined in terms of q, but that corresponds every time to a certain psi, which is a velocity or distance. Okay, so this scaling says, okay, the particles are such that their mean velocity has been of the order of Peclet to 1/4. And what is happening is that to solve this problem, you have to solve in the interior. What is happening is that the very fast averaging is happening along streamlines. So you end up with having to solve a problem for phi as a function of just the stream function. So it just varies across streamlines. So what you get is, this is the eigenvalue problem that you get. F is my eigenvalue, essentially by taking the full eigenvalue problem and then averaging it along streamlines. There's quite a bit of literature where these kind of things appear. You solve this inside the cell, that gives you a relationship between the function and its derivative on the separatrix, and then you have to kind of work out what's happening in the boundary layer near the separatrix. And fortunately, what's happening is exactly what's happening for the homogenization regime. Okay, so we have been able to recycle the Sowar solution to this problem. And Sowar tells you essentially that there is this relationship. So you match the two, and you get the eigenfunction. And so I should stress that homogenization is actually a sub-regime of this one. Okay, so homogenization is really a kind of a very thin layer in parameter space. So just to convince you that we've done our job properly, this is showing this f, this eigenvalue as a function of the rescaled q. And so in the usual way, the symbols are the numerics and the curves are the theory, and so they match. And so what you see, for instance, is that so the circles and the crosses correspond to different orientations of q. And so what you see is that for this parameter not too large, the dispersion is indeed isotropic, for instance. And then anisotropy shows up in the fact that the f that you get differs between essentially particles which are along the axis, traveling along the axis, and those traveling along the diagonal. So that's one regime. The next regime is sort of more amusing mathematically. There the concentration is essentially 0 in the cell interior, and then you have to solve only in the boundary layers. But the interesting bit is the fact that there are jumps in the eigenfunction at each corner. Okay, and those jumps have a kind of funny scaling, which I wrote here. Okay, and so you can boil down the problem to the dynamics in the boundary layer is just that of a heat equation, where time is actually the coordinate along the separatrix. So you can boil down everything to heat equations, and we know how to solve heat equations. So essentially, you can reduce the problem to just the profile of the concentration just upstream of each corner in one cell, maybe in 2 cells. So you end up having to solve an eigenvalue problem for 8 one-dimensional functions. Okay, so it's still something you have to do numerically, but it's much, much simpler than the original eigenvalue problem, conceptually at least. And so there are interesting observations. For instance, when Q is large enough, you get a very explicit form for F. And then for the experts, they will recognize the cumulant generating function that you get for random walk on a lattice. And this parameter here is the waiting time. Okay, so the time that particles between steps. And so that has a very easy interpretation, which is that in this regime, particles travel on the separatrices. They have a really hard time sort of crossing stagnation points, because stagnation points, there's no velocity, so they have to rely entirely on diffusivity to make the crossing from one cell to the next. Once they are away from stagnation point, they kind of take the velocity and they can move very quickly to the next stagnation point. They have a hard time there again. And if you just do a simple one-dimensional calculation, you'll find that the time it takes to go through stagnation point is of this scaling. Okay, so essentially you can summarize dynamics by saying you just jump from one stagnation point to another, a nearby stagnation point, but you have to wait quite a bit at the stagnation point because you have to rely on diffusivity there. And so there again, I mean, okay, you probably can't take this in, but again, is this function f as a function of q in this regime, and now we see that there is some sort of anisotropy. So I should say, okay, so this function is linear in q once you fix the sign. If you take the Legendre transform of a linear function, what do you get? Anybody paying attention? Yes. Well, you get a vertical asymptote. Okay, so this is telling you that my function g, my rate function, has a vertical asymptote, which is telling me that there's a finite speed of propagation in this. Okay, which is what you get for a random walk over a lattice. I should do something here. This doesn't seem good. Okay. So you get a finite speed of propagation for random walk on a lattice for, I think, obvious reasons, right? You cannot go further than taking all your steps in the right direction. So you get this is only an approximation. Okay, so it's telling you, if you look, this is g rescaled in a suitable way. So this is essentially the log of the concentration. So the crude asymptotics tells you that there should be vertical lines here. In fact, there's a logarithmic correction which we can compute. Okay. And then the final regime is this one where you can recover the rate function directly using an action principle, a minimization principle. So there are two ways of seeing this. So either you take this eigenvalue prime, which I showed you, and you introduce some sort of WKB type of solution. And then what you find is that the best characterization of the eigenvalue is in terms of a minimization problem. Okay, so it's an interesting example which I had not seen before, where you do asymptotics, but at the end, the best way you can write the solution is in terms of a minimizer of some function. Okay, so there's a paper there which explains how this works. Or it's even simpler to just return to the advection diffusion equation, observe that this is the Freidin-Wenzel type of regime, and so you can then compute this rate function as this limit. So you have to look for all trajectories which are going to take you from the origin to wherever you want to end. Right? So you fix the speed, the kind of average speed, and you say I'm looking for all trajectories which end up there, minimizing this kind of cost. So you do that over time t, and then you divide by t and take the limit t going to infinity. It's kind of natural thing to do. That gives you your rate function. Now this is a bit complicated, but in the case of the channel configuration, so just one row of cells, you can actually convince yourself that you can take t to be a multiple of a period, so you can limit yourself to periodic solutions. So then you end up doing this minimization procedure looking only at periodic solutions, and that's very easy. So it's an hour of work with MATLAB to code that up. So we've done that for this row of cells. So ignore the colors; they're about front propagation. here is an example of a trajectory which minimizes this functional. So what it is saying is that the probability for a particle to go from here to all the way to here is completely dominated by the single trajectory which minimizes this action. Right? So there's just one way of getting there, but it's only happening in this regime. Right. And so as I mentioned, there is this sort of nice correspondence between pure advection diffusion and then advection diffusion reaction, when the reaction is this FKPP type of reaction. So you can deduce front speed for FKPP from the knowledge of this G just by solving G of the front speed is equal to this Dam-Köhler number. So this is simply the non-dimensional version of what I showed before. Dam-Köhler number, is the ratio of the reaction rate. This alpha was reaction rate to the time scale of the velocity. So it's just to show you that we've essentially covered the whole spectrum of parameters. So this Dam-Köhler number can be also sort of as a distance from the origin. So essentially it's a proxy for it. And so what I'm showing here is, as a function of Dam-Köhler number, the front speed for different values of the Peclet number. So we assume that this Peclet number is large. We don't assume anything from the Dam-Köhler except that we will have three regimes depending on the relative size of Dam-Köhler versus Peclet. Okay, and so the black curves are exact solution. Well, sorry, numerical solutions, but you can think of them as being exact solutions. And then the asymptotics is made up of the blue curves, red curves, and then yellow curves, which you don't see very well there, but you'll see next. And so you can see that as the Peclet number gets large, you have this nice matching happening, okay, between one of the regimes and the next regime, where they kind of overlap nicely, so that there is no gap left. And the same is true nearer to the origin. So for smaller Dam-Köhler, you have the third regime in yellow. And you can't see anything, but the yellow curves for large Peclet kind of meshes nicely with the blue curve. Okay. Right. So that leads me to my conclusion. So I've discussed the fact that large deviation theory, as most people know, is a way of going beyond the central limit theorem. So what it is telling you is that instead of thinking that everything is Gaussian, you should maybe think that in the long time limit, everything has this form with a certain rate function. So then the interest is finding this function rather than just a single number, this diffusivity. So for this problem for large time, large deviation, you can find the rate function G by solving an eigenvalue problem for its Legendre transform. So both F and G, they are Legendre transform from another, so you can think of them as equivalent. They describe probability of rare events. And so there is this fact that for this kind of reactions I was looking at, rare events do control from speed propagation. Okay, so it's a nice order 1 manifestation of rare events. So for the cellular flows, I've shown you the results that we got in the limit of small diffusivity. So what I didn't show is that, so I talked about 3 distinguished limits. So in all those limits, in fact, the results that we get are still kind of semi-analytic in the sense that we still need a computer to solve the asymptotic problem. There are big regions in between, kind of intermediate regions, where you can actually come up with solutions which are completely in closed form. Okay. What I haven't talked about is the fact that you can also apply this to even simpler flows, which are just shear flows. And what you find then is that you generalize Taylor dispersion, so just dispersion along the pipes, if you like, when you have a pipe flow. So you can make interesting observations. The fact that, for instance, Taylor dispersion, which is a diffusive approximation, overestimates dispersion. So it tells you that there are particles when in fact there are none. And then something which we are working on, or are thinking about working on, are random flows. So you can try to play the same kind of games with flows which are random, either time independent or time dependent. And so there are in fact 3 references here, which are in various stages of progress. Okay.
Question? Yes?
I have seen that you mentioned functional and the extreme event, it's actually the instanton of that function. My question is why not using Martin-Sijarow's functional, which is a classical one for a stochastic system, and that would probably give explicit form of the instantons, probably like kings, which would allow to make even a statistics of these jumps. Because ideally you have, in another language, every center of a cell in your potential is a vacuum. And you have transition between vacua. And this is realized by instants, of course. And I think this...
Well, that's not of course, for instance, right? So, I mean, instantons in my problem are only relevant to a very extreme regime, actually. Okay, so there's a regime where cells are empty and yet instantons, at least the way I understand them, have nothing to do with the solution. Maybe I should stress, I mean, is that here we're doing asymptotics, right? So we're really starting from a full problem to derive a solution. We're not modeling things.
But you can have collection of instantons. I mean, you can have a particle which goes extremely far by a collection of kings.
Okay, I don't know what you have to tell me what you mean, so we can talk. Okay.
The Martin-Sijarow's formalism and this finding van der formula are just equivalent.
Right.
I
maybe
will say that.
Yes, sir, I think so. Are there other questions? Maybe can I ask a question also? Was there another?
I want to ask.
Oh, sorry.
Generally, what we do in the concentration equation, we use minus and the parameter, chemical reaction parameter, in the with the negative sign. You have taken alpha C into 1 minus C. Is there any specific reason to take in that way?
So you mean the FKPP?
Or it is only for the cellular flows?
I'm not with you. You mean the FKPP?
Concentration equation.
Yes, with chemistry?
In the very beginning, in the mathematical model you
Getting there.
have taken.
Lots of transparencies.
Yeah.
This one?
This alpha C into 1 minus C.
Yes.
This is only for the cellular flows?
No, I mean, this is the FKPP equation for any flow. What worries you? This is a standard FKPP equation, I'm quite sure.
I will ask you later.
Okay.
Questions, have you been thinking, I mean, again, without a reaction term, about how to, in such systems where you can also compute mobilities and not only diffusivities? In terms of, suppose you add a small, very small external field driving the particles in one direction, what would be the somehow the velocity or the current?
No, I'm not quite sure. You have to explain your language to me. So essentially, I mean, just to maybe stress what we've been doing essentially is to find the Green's function of this equation in the long time limit. So then everything which depends on this Green function can be computed.
If not, yes, please.
I mean, I'm not. It may be very naive, but probably for when you are far enough, what happens in every cell is independent from each other. So, if it is the case, you should expect your G to arise from something like the Kramer theorem, or what happened for each individual cell.
I mean, the cells become essentially irrelevant. Yes, I think that's right. Yeah.
You can still decompose a long path as a sum of
Right.
contributions from different cells.
Yes, I haven't
And
really.
you
So
can consider them as independent.
I suppose in this configuration, for instance, this boils down to saying that we solve a periodic minimization problem. So the optimal trajectory is actually a periodic one. Right. In 2D, you can only periodize this problem if the angle is right. Does that make sense?
All right, so thanks again.